be taken up by the test and that. Then after that, there's only 3 more weeks before the Easter break. So we do need to keep going and make a start on this final chapter. So this final chapter is quite different to all the other material we've been doing on calculus, on differentiation and integration and so on. This is quite different. This is more in the realm of what's generally termed discrete maths, perhaps. So it'll have quite a different flavor to some of the stuff we've done up to now. And it's kind of just an introductory chapter. There's a whole third-year course, third-year unit on group theory, which I teach, and that investigates the subject in great depth and works through a lot of the theory and looks at lots of applications of it. For us now, at the end of this first-year unit, we're just doing this as a kind of an initial introduction to some of the concepts in group theory. As I've said, this feels quite different to a lot of the other stuff we've been doing, and it's more abstract in a way, or it has the potential to be a lot more abstract. So this is on page 59. So talking about groups generally starts with the group axioms, or, well, maybe they shouldn't really be called axioms, but these are the defining properties of a group. So we'll have a short look at these, but then I'll spend the rest of the lecture showing you some in-depth example. Working through an example of something you probably haven't seen before, and trying to point out where these various parts of the definition arise in it. Okay. So what is a group? Well, very generally, a group is a certain set G, so a certain set of objects. Could be infinite, could be finite, and okay, I mean, it's just that it's non-empty, that there's something in there to talk about. And you have what's known as a binary operation. Now, I'll give you some more examples of a binary operation shortly, but in brief, a binary operation is a way to take pairs of elements, ordered pairs of elements from the set, and combine them together to produce a third element. Now, you're very familiar with binary operations. Every time you take 2 numbers and add them together to produce a third number, you're carrying out a binary operation. Every time you take 2 numbers and multiply them together, you're carrying out a binary operation. It's a way to take a pair of elements, an ordered pair, so you have a first element and a second element, operate with them together in some way, add them together, multiply them, or many other different types of things, to produce a third similar kind of element, a third element from the set. That kind of thing is termed a binary operation on the set. Now, you can have lots of sets with lots of binary operations on them. A group is a set with a binary operation that is quite well behaved. So is quite ordered and quite, follows definite trends mathematically, and is quite well, behaves well, has good structure mathematically. Now, what that means exactly is contained in these 4 group axioms, or 4 parts of the definition of a group. So a group is the set, together with the operation on it, because you could have the same set with many different operations. You could have many different groups on the same base set, so to speak. But it's a set and an operation which satisfies these 4 properties. First of all, it's closed with respect to the operation. And that means, so we're using our universal and existential quantifiers here. What closure means is for every pair A and B in the set G, the product, so we generally refer to the result of operating with A and B as the product of A and B. It won't always be exactly the multiplication of numbers A and B, but in general we refer to it as the product, or A star B, or the product of A with B. So closure says, well, when you take 2 elements and take their product, you always stay within the set. So the set is closed. You never pop outside the set by taking products of elements of the set. Second property is something you've met, certainly something you talked about when you talked about multiplication of matrices and addition of matrices, and associativity. We talked about it in terms of function composition as well, I think. associativity, and that says, well, you see, a binary operation by definition is a thing that operates on pairs of elements. So if you have a triple of elements, A, B, and C, you want to mush them all together with the operation in that order, well, there's two different ways to evaluate it, you see. You can either first take the product B times C, and then once you know that, take the product of it with A. That's on the left-hand side of the equation. Or you can do what's on the right-hand side. First take the product of A with B, evaluate that, and then take the product with C on the right with A times B. Well, associativity is when, for every triple of elements A, B, C, those two ways of evaluating the triple product always give you the same answer. That's when the operation is associative on the set. Okay, and that's a very nice operation, a nice property to have. It means that a triple product is unambiguous. Okay, because when you first write down a triple product A times B times C, you could be referring to either of these different methods of evaluation. So if they gave you different answers, then the triple product A times B times C wouldn't be uniquely defined. So associativity means that there's no ambiguity there. You can multiply together three elements, and whatever way you evaluate it, when they're in that order, you always get the same thing. Now, if an operation is associative on triples of elements, it's automatically associative on any finite list of elements, okay? So just by iterating this property, or by applying this property a number of times, if it's associative on triple products, it will also be associative on products of any finite length, okay? So that's property 2. Those are nice, well-behaved properties or properties of a well-behaved operation. And then 3 and 4 kind of go together. 3 says, well, there's one special element in the set called the identity element. Okay? So there's one special element in the set called the identity element. It's very special, and it has this special property. Now, we normally term it E, which I think comes from the German word eigen, which kind of means self or one or some notion like that. Eigen. It's the same eigen in eigenvalue and eigenvector and so on. So an identity is this special element E, such that when you take the product of it with any A in the group at all, on either side, so E times A or A times E, you always just get A. So it leaves it unchanged. And then property 4, to go along with that, is the existence of inverses. For every element A in the group, there does exist an element which we denote here A superscript -1. You read it in English as A inverse. So for every A, there does exist another element A inverse, such that when you multiply the A and this other element A inverse together, you get back the identity element E. And in certain special cases, this A inverse element could in fact be the same element as A. So though you could have a self-inverse element. So that's the definition of a group. That's what a group is. But now it's a very abstract thing, that definition there. It's not referring to any specific mathematical objects there. It's not referring specifically to a system of numbers or a system of matrices or a system of functions. It's just an abstract pattern describing certain kind of common features. And when we see those features on any particular system, we'll agree to call that system a group. Okay? And then what group theory is, because it turns out when you look into it, this pattern of properties crops up all over the place. Okay? So many different areas of mathematics, many different types of mathematical object fit with this pattern. So it's a very fundamental idea. Having an operation on a set of elements is extremely fundamental. And almost all of mathematics fits into that pattern. I mean, some kind of system and some operating procedure on the system. It's just so basic. Now, not every such system is a group. These are very special properties, as I say. These are properties that say the operation is behaving very well, very systematically. But even so, they are still very permissive, these properties. So there are lots of different examples of groups, as I've said, in many areas of mathematics. A group theory is really just the study of the different types of groups that you can have. and understanding the whole universe of groups that kind of grow out of these defining properties. Working out what kind of groups can exist, what kind of groups necessarily don't exist, and working out classification schemes. Some way of classifying or ordering the whole universe of different types of groups into certain logical families. Just like the periodic table of elements, chemical elements, gives you a very ordered, logical, structural way to view all the possibilities that there are for the formation of atoms. You know, every possible atom fits into one of those little squares on the periodic table, and it's been, most of them have been observed. I think maybe there's still a few configurations that haven't been observed yet. But they've worked out all the possibilities that there could be, and we understand them quite well and organize them into certain families and so on. Well, group theory sets out to do a similar thing, not with atoms of matter, but with groups, systems, elements of sets of elements and operations on those that follow these elements. Okay? Okay, so that's all been very abstract so far. So for the rest of the lecture, we're going to talk more specifically. We're going to look at specific examples of types of groups and refer back to these properties a number of times and show where they crop up and so on. Okay? And then in the later lectures, we'll do a little bit of group theory. We'll do a little bit of working with the abstract definition, working out some of its logical consequences, and looking in more depth into certain types of groups. So, these are examples of groups. Well, first of all, a very, probably one of the most familiar or easy to write down examples is the system of the integers under addition. Okay? This is the integers under addition. So plus, regular primary school addition of numbers, the thing you're very familiar with, that's the binary operation here. You take any two integers, e.g. the two random integers, 7 and minus 13. Take two random integers, you can always add them together. Minus 6, is it? You always add them together, and you do indeed you always get another integer. Okay? So it's clearly a binary operation on the set. Any pair of integers, you can add them together. The result you get out of it is always an integer. You never suddenly magically get a fraction, get a non-integer fraction out of it. Or you never suddenly obtain a function having added two integers together. You add two integers and you get another integer. Okay? So it's clearly a binary operation on the set. Clearly closed. It's clearly a binary operation. The binary word there, remember, binary refers to two-ness. So the binary is referring to the fact that there's two inputs into the operation, a left element and a right element. You can have ternary operations, things that take three inputs, but you don't meet them normally. So it's clearly a binary operation, clearly closed. Is it associative? Yeah, it's associative. When you add together three integers, doesn't make a difference in what order you evaluate. Whether you add the first two together first, and then add on the third, or whether you add the second and third first, and then add the first to that. Okay? So adding up any finite collection of integers is unambiguously defined. It doesn't make a difference in what order you evaluate the little binary additions. As long as you add up all those integers, you're always going to get the same answer. The associativity is well known. Now you can ask, well, how do you, really, can you prove associativity? Well, Yeah, you can prove associativity, but before you prove it, you have to very carefully set up an axiom system for the integers. You have to very carefully specify, well, what exactly is this set of, this kind of doubly infinite set of whole numbers. You have to very carefully specify what it is. You have to very carefully specify what the operation is. And when you lay down some more fundamental logical axioms, you can prove that associativity follows from them. But for our purposes now, we'll just observe that associativity, it's a very familiar property of addition on the integers. What about axioms 3 and 4, the identity element and inverses? So what's the identity element in the integers? Ah, 0. Somebody said 1, but for addition, the identity element is 0. So there is a special element, yeah? So z plus has 0 as the identity element. So look at the axiom for identity, axiom 3. Observe that this is correct. Axiom 3 says there exists an E in G. Okay, well here's our 0 in Z. There exists some element E such that when you take the product of it with any other element, do E star A or A star E, you have to always just get A. Well, 0 clearly plays that role in relation to addition. e.g., stick with the minus 13. You add 0 to minus 13, what you get? Minus 13. You always get the same thing. You get the same unchanged value. And inverses. Inverses are also present. The inverse of an integer z is minus d. Okay, so every integer there's another associated one, minus it. Then when you add the two together, you get 0. You get the identity element. There's one special element which is self-inverse here. Which is that? Which element is its own inverse in this group? 0. So there has to be an inverse for 0 as well, because the inverse axiom says every element has to have an inverse. So what's the inverse of 0? Well, 0 is its own inverse. When you add 0 to 0, you get 0, which is the identity. So that's a nice example. Notice also that plus is what we term commutative on Z. I.e., if you take any integers Z1 and Z2, you always get the same thing no matter what order you add them in. So for every pair Z1 and Z2, when you add Z1 and Z2, it's the same as Z2 plus Z1. Now that is not a group axiom. It's not part of the definition of the group. So immediately the universe of groups splits into two families. One where the operation is commutative, symmetric like this. The other which is a family of non-commutative groups. So we haven't met a well, I'm going to show you an example. So we'll be on the lookout for an example of a non-commutative group. Okay, well we won't dwell too long on the integers under addition. So what we're doing there is just observing that is a system which satisfies those four axioms. Okay. What about, now before we specify the set very carefully, let's just speak in general about multiplication of numbers. If we want to make a group, be a bit vague about what the set is, some set of numbers, but we want to use the familiar operation of multiplication of numbers. Well, is it associative? If you take a product of three numbers, product meaning you're multiplying three numbers together, yeah, it is associative. We're well familiar with that. Right? It doesn't make a difference in what order you evaluate the individual binary products, you'll always get the same thing. Is there an identity for multiplication? One. See, I gave you the opportunity to say one, but you were too slow. Yeah, one. Sorry, I was putting mine. Yeah, one is the identity for multiplication, the number one for multiplication numbers, and the inverses are. What's the inverse of the number a? Which number is the multiplicative inverse of a? 1 over a. Yeah, the reciprocal. Now, does that work for every number?
No.
No. Which one is the problem?
0.
0. 0 is the problem. 0, it's a perfectly good number. It can take part in multiplication. You can multiply numbers by 0, fine. You always get 0. It's kind of a killing element in a way with regard to multiplication. But so it can take part in multiplication, but it doesn't have a multiplicative inverse. There's no number such that when you multiply it by 0, do you get the multiplicative identity 1. So whatever set of numbers we write down here for our group, we can't include 0. We have to get rid of 0. But every other number is okay. Every other number has a multiplicative inverse. Okay. So the identity should be 1. The inverse of a should be 1 over a. Of course, that only works if a is non-zero. So, for instance, and associativity is well known, we'll just say. So, for instance, the set of non-zero real numbers under multiplication is a group. Okay? This group, this set together with that operation, so it's every real number except the number 0 under multiplication, that is indeed certainly closed. You take two real numbers, multiply them together, you get another real number. You don't suddenly get a matrix or something. You always get an object at the same time. It's associative. There is an inverse. Sorry, there is an identity, the number 1, and everything in the set are less 0. So this is set of difference, so we're subtracting the set containing 0 from the set R, instead of all non-zero real numbers. Is that the symbols Saeed used for set difference, or did he use a minus sign? So some books will use a backslash like that for set difference. So this is the set R except everything in this set, so except 0. Okay, so that's a group. And again, it's commutative. So there's there's maybe two of the most immediate examples of groups that are most familiar to people. Now there's one more group which I'd like to concentrate a bit more on in the remaining time, but for the moment, and we'll see more examples of these as we go through. But for the moment, so lots of groups arise in relation to addition and multiplication of matrices. So I'm just speaking in general, I'm not being very particular about which matrices or whether it's multiplication or addition, but there are various groups you can form out of sets of matrices under either addition or multiplication. More abstract number types. More abstract number types, so complex numbers, quaternion numbers, algebraic, integers, lots of these terms that you don't know what they mean. But there's a whole menagerie of more abstract number types where you've got operations that grow out of addition and multiplication, and they so lots of number type groups. And then another whole important family or area where groups arise is groups of certain functions under the operation of composition. And that's really very, very important example. So functions can represent any kind of process, very general, universal terms, and composition, remember we talked about in chapter 3 on functions, composition is the operation that you can apply to functions, and it exactly corresponds to performing different functions in sequence. So performing one function on the outputs of another, chaining together different functions, chaining together different processes, and building compound functions or compound processes out of it. Right, is there any trouble there reading what I've got there? Any word unclear? Okay. So we've got addition and multiplication of matrices, more abstract number types, complex numbers, quaternion numbers, algebraic integers, just a few terms I'm throwing down there. And then another important, this is a huge family of groups fall under this description, groups of certain kinds of functions under the operation of composition. Okay. And this is where you get your non-commutative examples from, okay? Because composition, performing one thing after another, is inherently a non-commutative operation. Okay? And that's just true in general. You've got processes, and you do them in different orders. In general, that's different, produces different effects. I have an example of the cake. Remember the cake? I was mixing the cake and baking the cake. That was a different example. Okay. It's one of these kind of groups we're going to look at now. So our next example will be, I think, unfamiliar to you in the way it's presented. So this is called the dihedral group D3. That's what its name is. And this is the group of symmetries. The group of symmetries of a regular triangle. That's what the elements in the group are. The objects in the group are symmetries of a triangle. And the operation is function composition. So here's our regular triangle. Assume that that's regular. We'll think of it centered on the origin in R2. So this is my triangle centered on the origin in R2, in the plane. My origin there in the middle of the triangle. And a symmetry, so what do we mean by a symmetry? A symmetry is a function well, it's a certain kind of function from R2 to R2. So it's a transformation of the whole plane. A certain kind of one. Which leaves the triangle unchanged as a set of points. So it might move around individual points. It might move around individual points of the triangle, but it's going to leave, there'll still be the same triangle sitting there afterwards, after you apply the transformation S. Now there are 6 symmetries there are 6 elements in D3. I'm being a bit vague about exactly what the qualifications on functions SR2 to R2. It's only certain kinds of natural transformations of R2 that we're going to consider. So what can you do to a triangle to make it unchanged, to maybe move the triangle around, but afterwards it's the same triangle sitting there, and that these exploit some of the natural symmetries that the triangle has. What kind of things could you do to the triangle? Or do to the whole plane, which leave the triangle unchanged? It's a regular triangle. What does that mean? Flip it. Rotate it. That's the word, yeah. So there are rotations. Well, flip is the other kind of one. Flip suggests a mirroring reflection, which is the other kind of thing, which we'll come to in a moment. So rotations. There are certainly, you can rotate the triangle, and it's still the same triangle. So you can rotate it 1/3 of a full turn. The individual points in the triangle will move to different locations, but it's still the same triangle sitting there, centered on the object. You can rotate it by 1/3 of a turn. You can rotate it by 2/3 of a turn. Are there any other rotations? Well, maybe if you rotate it again, you rotate it 3/3 of a turn, but that's rotating it a full turn all the way around. Well, that's the same as not doing anything. We still call that or consider that a certain kind of rotation, but that's the identity element. So the identity element is doing nothing to the triangle. It's just the identity transformation on the plane, sending every point to itself, leaving everything unchanged. That's the identity symmetry. Every object has the identity symmetry. So there are rotations. So R and R squared, and we'll include E, the identity, in there, which is also equal to R cubed. So this is where R is rotation about the origin. And let's make it specific by 2 pi over 3 radians. And just to pin it down, we have to say which way we're going, clockwise or anti-clockwise. Well, the default direction by convention in mathematics is to go anti-clockwise. Something against the clocks mathematicians have. Want to go the opposite way. There's probably some website somewhere where they sell clocks that go the other direction to appeal to math students. Maybe. So there's three rotations. Rotating it properly by either 1/3 of a full turn or 2/3, and then either doing nothing to it or rotating it by 1 full turn, or 2 full turns, or 3 full turns. Well, they're all the same transformation of the plane, just sending everything to itself. That's the identity. So that's 3 of the symmetries. The other ones are the reflections. There are 3 reflection axes of symmetry of the triangle. And all these axes go through a vertex on the midpoint of the opposite side. So there are reflections. For the moment, let's call them S1, S2, S3. Let's label these, label this one as S1, S2, S3. Okay, I'm labeling the reflection axes there. But S1 and S2 and S3 refer to reflecting the whole plane in those lines. Okay. It's clear, when you reflect the whole plane in those lines, the triangle as a whole is still sitting there in the same position. Okay? Some of the points move around. Michael was up here, will now be living over here and so on, after you reflect it in S3. But they are reflection symmetries of the triangle. And there are no other ones. There's no other ways to reflect the plane which leave the triangle unchanged. Because if you reflect the plane in any other axis, it won't be exactly the same triangle sitting there. The triangle will have moved to a different position. Yeah, be occupying different points. So these are our 6 elements. So the square there refers to R composed with R. The square and the cube, they refer to the operation of composition, taking R with R and R cubed and so on. So these 6 elements form a group with respect to composition. You might conceive of other ways to combine these functions of the plane to give you other functions, but that might give you other groups. But when you combine them using composition, you're forming the symmetry group. So the symmetry, so this is a triangle, but you can obviously see how we could do the similar analysis for any kind of regular 2D shape. You can extend it up to 3 dimensions as well. You could obtain the symmetry group. You can identify all the symmetries of any 3-dimensional object as well. 4-dimensional, 5-dimensional, 6-dimensional. So it's a very general idea, picking out the symmetries of some kind of object and forming the symmetry group. So the symmetry group, it not only identifies the different symmetries that the object has, but it also records, or it also has within it, the way they combine. Because with these 6 symmetries here, if we compose 2 of them together, so we perform one function on the plane, and then perform the other function after that, well, both of the individual symmetries leave the triangle unchanged. So the triangle will still be unchanged after you've composed it. So the composition of any 2 of these symmetries must be one of the other 6. Because we're confident that we've identified all the symmetries here. So we've got all 6 of them. So the composition of any 2, or in general terms, the group product of any 2, must be one of the 6. So to get a complete understanding of this group, you need to be able to understand exactly how the operation works. These products, we'll finish on this, these products can be shown in what's called a Cayley table. So Cayley table is named after this mathematician Cayley. Did work on group theory, but it's quite a familiar idea. It's simply a multiplication table for the group. So here's our group. Now, in a Cayley table, see here, because we're dealing with function composition, which is not commutative, we have to be a bit careful about what we mean. So if we've got an element Gj here, an element Gi here, the entry that goes, we use the same indexing that's used in matrices. So the idea is, in every entry in the table, we're going to put the product of the corresponding, the element of the row we're in and the element of the column we're in. But we need to be careful about the order. So if we're in row corresponding to the element Gi, and in the column corresponding to the element Gj, the product that goes there is Gi composed with Gj. Okay? Gi composed with Gj. We have to be careful here because function composition is not commutative. So we have to stick with the correct convention for the order. I don't know what your school was at. When I was in primary school, they got us to do this all the time with the numbers 1 to 10. Or some set of numbers, and you construct a multiplication table for them. Just to get us to bring in cornflakes packets, cook them open, and on the reverse side to do these things out, and then laminate them. They could have been teaching us, but they didn't. They just got us to do this all the time. Anyway. These parts of the tables I can just put down straight away. So what am I doing there? There I'm carrying out all the products with the identity. All these elements across here are E composed with R, E composed with R2, S2, E composed with S1, etc. But E is the identity element. It doesn't change anything. Similarly, when you do R squared composed with E, it doesn't change anything. So, you know, but I mean, there's 36 elements to fill out here. It's not completely random, of course. There's a lot of systematic structure that goes on in the table. So what's R composed with R? Sorry, 2R, or what's the correct way to say it? Not 2R. Just about, you've got the right idea, but a better way to phrase it. R squared. R squared, yeah? R composed with R gives you R squared. R squared means R composed with R. That's just the meaning of it. So, what do you get when you compose R and R squared? R cubed, or not 3R, or E. We've agreed to call R cubed E. See, this is the idea. All the entries in the table should be one of the 6 elements, shouldn't they? So when you compose 2 symmetries, you get a symmetry. So R cubed is correct, but we've got the name E, the identity for that. R cubed means rotating the triangle by 1 complete full turn, 3/3 of a full turn. Well, that's the same as not rotating it at all. It's the same transformation. So R squared composed with R will give us E as well. R squared composed with R squared, this entry down here, R, yeah. That'll be rotating it 4/3 of a turn, which is the same as rotating it 1/3 of a turn, which is back to R. Not so obvious is what this entry here is, R composed with S1. I shouldn't have drawn that box there, but anyway. What's R composed with S1 going to be? Well, it's not so easy just to come up with the answer off the top of your head. Now, there's 2 types of elements, rotations and reflections. Which type of element should this be? Should R after S1, should it be a kind of rotation or a kind of reflection? How do shapes in the plane end up after you've reflected the plane and then afterwards rotated it a bit? They're still fundamentally reflected. Rotating can't undo a reflection. So this should be a reflection. Now it's not going to be S1 because you've rotated it a little bit. So it'll either be S2 or S3. It's not so easy to do in your head. You have to kind of do a bit of investigation. So in order to do this, you can label the vertices. Which could no, let's not. I've used numbering on the reflections, so instead I'll just letter the vertices, so as not to confuse them. So we need to view this diagram in comparison with our reflection axes as well. So R after S1, so that says first we have to do S1 on it. So how do the vertices move around when you do S1? Well, S1 is reflection in this axis here. So C is going to remain where it is, and A and B are going to swap. Yeah. When you rotate it again, okay, it's still the same overall triangle, but when you rotate it 1 turn and a full turn anti-clockwise, this C goes up to here, this B moves down to here, and this A moves across to here. That's R. So this whole transformation here is R after S1. That's compositional. What single in one step, what single one-step symmetry is that? And you can tell you can tell by looking at the vertices. S3 is the correct one, because look, S3 is this reflection axis here, from the bottom left vertex through the midpoint to the opposite side. And you compare the 2 triangles, you see, oh, overall, B has remained where it is, and A and C have swapped. So yeah, this axis here which is the axis of S3, that's the symmetry that we've performed. So R after S1 is equal to S3. Very good. So that's what goes in this box here. So R after S2 has to be then, there's only kind of one option for R after S2. Oh no, there's two. It could be getting towards the end of time. Okay, so let's quickly work out R after S2. So S2 sends this to A and CB, and then R sends it to A, C, B. So this is R after S2, and yeah, it is S1. That'll be S1 and S2. Okay, so an exercise for you in the meantime then is to complete the table. Okay, we'll continue our discussion of groups. Maybe a little bit tomorrow if we dispense with the revision early on. Otherwise, after the test.